Okay, we're going to talk a little bit about some nonlinear effects, and unfortunately it's October and the lighting is such that 5:30 I had to turn the lights on. The camera doesn't seem to like that, but bear with me. Just use the video as audio to look at while you're going over the lecture notes. The other two today looked pretty good, I thought. Anyway, in a nonlinear effect, it involves frequency changes, right? So, for example, frequency comes in and it turns into two different frequencies, right? This might be called the pump. This might be called the signal. This might be some acoustical or phonon type of wave. And these are usually labeled by chi, a chi of various orders. So it might be chi to the n, a chi 2 process, a chi 3 process. It just tells, in here just tells you how many waves are involved, right? If there are only two optical waves involved here, then this would be a chi 2 process. Not a real key point. Let's get on with the key ones. Rayleigh scattering is a type of scattering, and so are Raman and Brillouin scattering. But stimulated Raman and Brillouin scattering are nonlinear processes, whereas Rayleigh scattering is not. This is the thing I mentioned that causes loss in optical fiber as you go to the ultraviolet frequencies. People have called these processes as elastic scattering as opposed to inelastic scattering. The way I like to remember that is, for elastic scattering, there's no frequency change, there's no transfer of energy, right? So in the fine print here, energy we know is Planck's constant times frequency. This h bar thing is just Planck's constant divided by 2 pi. Is handy sometimes, just as omega is 2 pi f is handy sometimes. Right? So by energy conservation, we'll tell you how the frequencies change. This one comes in and it turns into those two. So for this process, by energy conservation, I'm in a fine print here, so I can abbreviate. Energy conservation would tell me that the frequency of this pump turns into the frequency of the signal plus the frequency of the acoustic wave, if that's an acoustic wave. And I'll draw the energy diagram here in a moment. This is kind of an aside. So let's go ahead and label it as an aside, although you know that stuff. End of aside. So getting back to Rayleigh scattering, what is this elastic scattering? I think of super ball bouncing off the planet Earth. Does the Earth recoil? Yeah, but not by much of a noticeable amount, right? Energy is always conserved, but and so is momentum. But the momentum change of a super ball is trivial compared to the velocity change in the planet Earth, because the mass of the Earth is so big. So elastic scattering, there's none of this energy transfer stuff going on. In other words, no recoil is another way of thinking of it. All right. Super ball bouncing on Earth. I don't notice that the Earth recoils. Okay. Rayleigh scattering was the process by which the loss gets dominated into the UV. D here is the size of the atoms. this is the part that made it go with a very small wavelength. I'm going into the ultraviolet. So in an optical fiber. That part is due to Rayleigh scattering. These other things are other processes, water absorption, etc., and what happens in the infrared. Right? But Rayleigh scattering is what makes it so that you get tons and tons of loss as you try to go into the ultraviolet. Raman and Brillouin scattering are examples of inelastic scattering where there is a transfer of energy. So let's draw that energy diagram now. We saw these before, but rather than having a whole bunch of levels up there at the top, little spin flips, we have a whole bunch of energy levels down here that are caused by vibrations. So the pump comes in, giving me an energy transition of that big, and then this drops down, giving me the frequency of what is going to be a signal, and then we have these vibrational modes. So that's where the rest of it goes into. The crystal itself recoils, right? So there's energy being transferred. Because there's energy being transferred in this recoil, there's a frequency shift, right? So if this is a bunch of junk I don't care about, one color came in, a different color came out. One frequency came in, a different frequency came out. There's a frequency change in a nonlinear process, right? That other energy could be vibrational energy. And these are called phonons as opposed to photons. And in the case of Brillouin scattering, these are sound waves. These are acoustic. And being sound waves, these travel at the acoustic velocity, the speed of a sound wave. Okay? So one big difference between these two processes is that in the case of, Raman scattering, with an R, then these so-called phonons are called optical because they travel at the speed of light, c. When I'm coming in at very low power, there's very little loss. The process doesn't do much, nothing much happens. When I go to high power, then it becomes stimulated. Hence the S in front of Raman scattering or the S in front of Brillouin scattering. Right now it's a stimulated process. The scattered power grows exponentially once you're past some threshold. Right? Here's some of the differences between stimulated Brillouin and stimulated Raman scattering. In Brillouin scattering, the wave only comes backwards. Right? So this is the case where, as I said, you want to send a lot of energy down the fiber, but as you crank more and more energy into it, suddenly it all starts scattering back at you. That's Brillouin scattering that's making that happen. There's a frequency shift, total frequency shift. The difference between these two frequencies is like 10 gigahertz per Brillouin scattering, whereas it's about 10 terahertz for Raman scattering. 1 terahertz being 10 to the 3 gigahertz. I wish the students in the next room would go outside to talk while I'm recording a lecture. Hang on. Let me pause.